Welcome to a video on the finite gain of op-amp. Okay, so first we're going to look at what do we mean with finite gain, then how do we revise our gain equations for our closed loop amplifiers. Then I'm going to let you do some calculations and design, and lastly we will look at some simulations of these solutions. So, again, we usually assume that the op-amp is ideal and that it has infinite gain. This is one of the assumptions that we make for ideal op-amps. Now, this assumption is not ideal in the sense that op-amps typically have 100 to 140 dBs of gain, which is a very high number. So, in mathematics, if you divide something by a huge number, you typically get 0. So this is why taking it as infinite is the norm. But there is op-amps out there that does not have an infinite amount of gain, and you get these in the 40 dB to 80 dB range, so 100 to 10,000 volts per volt gain, and that has influence on the output. So you can design your feedback resistors for a specific amount of gain, and when you run the circuit, you will find that you're not even close to the gain that you designed for. So we need to revise our gain equations to compensate for the fact that our op-amp does not have infinite gain. So how do we do this? We need to let go of one of our assumptions. And then lastly, how can we modify already existing circuits to compensate for this error? So in the figure here on the side, to answer this question here, we will do this in the simulations as well and the problems, is if a circuit is already on a board, you can modify resistor 1 by soldering an extra resistor on top of it in parallel to fix the gain, because you decrease resistor 1 size, the gain will increase. But this is not a nice option for an inverting amplifier because you decrease your input impedance by doing that. Or you can go through the effort, desolder resistor 1 and put in a smaller resistor, again dropping the input impedance. Or lastly, by replacing R2 with a higher value. So those are the three options that you have in existing circuits. Also, when you're just designing, replacing R2 and R1 is the best options, not the parallel combination. Okay, so redoing our gain equation. So the assumptions that the currents flowing into the op-amp here is 0 remains, but the one that we don't make is that Vn and Vp is equal to each other, and in this case equal to 0. We do not make that assumption. So what we rather do is we see, okay, our op-amp has output V out, and the input here must be some voltage then, which is multiplied by the gain. So Vn is minus V out over A, because this is the inverting terminal. So some smaller value multiplied by the gain should provide V out. And we just redo our equations from there on. So I1 is equal to I2 because the currents flowing into our op-amp is 0. So we write down our Kirchhoff's for I1 and I2. So basically V in minus V out over A, makes that a positive, is equal to minus V out over A minus V out over R2. Okay, and then we get the equation like this one over here. When we equate them to one another, then you multiply throughout by R2 R1 AV so that you can simplify your equation easier. Find your gain ratio V out over V in. And lastly, the addition of this step where we basically multiply by 1 is to get our amplifier in the form that we have minus R2 over R1 on top, which is our regular gain when just using feedback resistors. Okay, so the top is the gain that you're aiming for, and then the bottom is the adjustment with the amplifier's finite gain. So this is called GV in our equations, is the gain that you want with your feedback resistors, and AV is the op-amp's gain. Okay, so if you take this equation and you make AV infinite, like the assumption said for the gain, then you will find that you are back at minus R2 over R1. Okay, so this equation right here is the one that we use when an op-amp has finite gain. Okay, for the non-inverting op-amp, we can do exactly the same. The input just moved, so we look at the differential of our amplifier. So V out is the gain of amplifier multiplied by V in minus V in, and we rewrite this into the format where we have Vn standing alone. So that is our first equation. Our second equation is the voltage divider that we are seeing here. So V out is being voltage divided to find us our Vn. That is our second equation. If we equate these two and we go through some mathematical steps, we end up with 1 over AV plus R1 over R1 plus R2. And again, we multiply this with our gain of our amplifier with feedback so that we can get it in the form of 1 plus R2 over R1 on top of our adjustment for the gain. So once again, if we make the amplifier's gain infinite, we end up with 1 plus R2 over R1. So we use these equations to compensate for the amplifier not having infinite gain. So if we have infinite gain and we want the amplifier with a gain of 50 volts per volt, this is where we start with the problem of today. You will typically choose a 56K and a 1K resistor to have a gain a bit larger than 50 volts per volt, right? So for the inverting, you would end up with minus 56, and the non-inverting, you will end up with 57. This is if our amplifier's gain is infinite. Okay, for the non-inverting, you could also go for the 47K, which will place you at a gain of 48. Depends on the application, if you will choose upwards or downwards. So there is some resistor choices. Now, let's say we want to use the LT1229 op amp in this application. Now, if you go and have a look at the data sheet, it says that our minimum and typical gains in dBs is 55 and 65 for this op amp. So converting the 65 to volts per volts, that is 1788. So this wouldn't be a problem for a gain of 50. But if we go and run the SPICE model in the simulation, we end up with the amplifier having a gain of 46 dBs, which translates to 199.5 volts per volts. Now this is the issue. Okay, 50 is much closer to 199. So we definitely need to redesign some resistors for this case right here. This, in the other hand, this 1778 would become a problem for gains of 100, gains of higher than 100. We would start to see the effect, but for 50, that area we will not see the issue there already. Okay, the issue will come with but higher gain choices. Okay, so we're going to use this 46 dBs in our calculations since I want to show you the effect in the simulator itself. Right, so the problem that I want you to pause this video on and go and do is that I want for the inverting and non-inverting amplifier that you need to calculate the resistors for 50 volts per volts using our finite gain of almost 200 in 3 different scenarios and for both op amp configurations. So first, calculate the replacement for resistor 1. Then redo it and calculate the replacement for resistor 2. And lastly, calculate a parallel resistor to resistor 1. So the first two is when you're just designing and you can replace parts, and option C here is when you need to mod a circuit. And choose E12 values for each resistor. So pause the video and try and do these problems using those two new gain equations. So if you need to calculate resistor 1, keep resistor 2 at 56k. If you need to calculate resistor 2, keep resistor 1 at 1 kilo ohm. And for this last one, keep both of these resistors the size that they are. Okay, so pause the video, and in the next slide I will reveal the answers. Right, so I went ahead and tabulated my solutions. So in the first case, I find that we should replace resistor 1 with 843 ohm resistor. So 820 is a good choice. That will make our gain a bit larger. For the second one, I calculated that the feedback resistor should be replaced with a 67k. So the closest is 68k's. And the parallel combination, 1 kilo ohm in parallel with 5.4 kilo ohms. So I made that a 5.6k. And I did the same calculations for the non-inverting amplifier. For this low amount of gain, you will see that the values are kind of close to our inverting companions values. So we end up with the same resistors for both. With higher gains, they will be even closer. But when we're working with low gains, around 10, 15 thereabout, these resistors will differ quite a lot. So, I hope you got the same answers as I have. If not, go and work at it. Practice is the best. And I will now jump over to my simulation. So in the simulation, I set up both amplifiers with the resistors for the ideal case. So if I run it, we will see that our gain is not 56 and not 57 like we anticipated. So if we run this, there, just under 4.5 volt output. So this is under 45, and this one is just below 45 gain. So that is really far off from the 56 and 57 that we do expect. Okay, so option 1 was to change this resistor with 820 ohms and this resistor with 820 ohms. Okay, so the blue is our non-inverting and the green is our inverting. So if we run this, we are just over 50 volts per volts. Okay, but in this case for the inverting, we reduced our input impedance. Not much of a change for our non-inverting configuration. Okay, so that is the first one. The second one is to make this 68 kilo ohms. These two will be more accurate or closer to 50 volts per volts. Let's run it. And the green one, so the inverting is on the dot and the non-inverting is a bit over, like we would expect. Okay, and the last one is the parallel connection. So let's just connect these resistors like so, run it, and there is almost no change in the simulation. So all three solutions actually works. Okay, and that is finite gain for op amps and how to deal with finite gain when the problem arises. Thank you for watching. See you in the next video.